Okay. Hey, everyone. Hope you're enjoying the talk so far. So before we dive into our presentation, I got a confession to make. So I used to work in a team of software engineers where our productivity was measured in story points. So obviously what happened, I think you already know what's coming. We started to inflate our estimates and we still delivered. So it looked really sexy on the leaderboards, but the other teams picked up quickly on it. So it kind of turned out to be a nonsensical experiment. So it's questions like this, problems like this. And after working for 20 years in the industry, not having good answers to that, we decided to set up a study together with practitioners and researchers at Stanford. It's an ongoing study to dive into software engineering productivity. We got contributions from more than 50,000 engineers. And before we go into the contents of our presentation, let's do a quick intro. So I'm Simon Obstbaum. I'm former CTO of Crunchyroll. It's a video streaming service for anime, if you heard of it.
Hi, everyone. My name is Yegor, and I'm a graduate researcher at Stanford. My work focuses on using data to make better decisions in software engineering. And in a past life, when I had some more hair on my head, I used to look after digital transformation projects for a large company with more than 6,000 engineers. Part of the research team, but unable to join us today, is Professor Michał Kosinski from Stanford. He is in the top 1% most cited researchers, and his research focuses on human behavior in a digital environment. He was the whistleblower behind Cambridge Analytica back in the day, if you remember that. And on top of this, he is a Stanford computer science postdoc. So today, we're going to be talking about a number of things. We're going to kick things off by giving you some more background on what motivated us to begin this research. Next, we're going to dive into the topic of output versus outcomes and why we think you need to measure both. After that, we're going to do a deep dive into our latest research. And in fact, we just published a paper in preprint earlier this week, which is available online. More on that later. Following this, we're going to take a look at some case studies, and then we'll finish things off with looking into what other topics are we researching currently. So before we begin, it's helpful to take a step back and get an understanding of what do teams nowadays use to measure productivity. Based on our research participants, we think this can be divided into 5 buckets broadly. There's lines of code, there's counting commits and PRs, there's story points, then there's also surveys, and lastly, there's DORA. Now, the problem with all of these is that they aren't effective and accurate at measuring productivity. Let's take a look at why and start off with an easy one, lines of code. So hopefully this one isn't a surprise for you or for most of you, but more lines does not necessarily mean more productivity. And the problem gets worse once you consider that different languages have different verbosities, which means that they're kind of hard to compare against one another. So if you use this as a metric to measure productivity, what you might incentivize is that your developers are going to start writing verbose and redundant code in an attempt to game this. The second one we have is number of commits and number of PRs. And here, the problem is similar. Since we're not looking at what's inside the commit or what's inside the PR, more commits doesn't necessarily mean more productivity. And once again, it can encourage artificially smaller commits and PRs, which at some point is going to have diminishing returns. So then this next one is story points. And as Simon was alluding in his intro, this is a subjective measure, which is very hard to compare not only within teams inside a company, but let alone with teams across companies. And so because of this, it's not, delivering more story points doesn't necessarily mean delivering more, let's say, features, right? It's not really a good measure of productivity. And if you use this metric, you might be incentivizing your teams to inflate the number of story points that a task may take, just as Simon might have or might have not been doing in the past. All right, so then this next one is an interesting one, self-assessment surveys. We ran a small experiment with 43 software developers, not a huge sample, but big enough. And we asked them to self-assess where they thought they stood in terms of how productive they were relative to the engineers globally on a scale from 0 to 100 in 5-point intervals. Next, we measured those engineers with our metric, and we got, as you can see, quite a low correlation. Now, you might pose the argument that, hey, well, maybe your metric is wrong, and that would be a valid critique, which we will explore a bit later. But for now, based on this experiment, we can suggest that self-assessment surveys are an ineffective predictor of productivity as measured by our metric. We also found a few interesting insights, such as, on average, people misjudge their own productivity by 30 percentile points, and only 1 in 3 developers comes within a quartile of accurately estimating their productivity. This can be the difference between being above average and bottom quartile. We think surveys are a great tool for measuring certain things, such as, developer happiness and experience, but we advise everyone to be careful in using them to strictly measure what might be perceived as productivity, because there's lots of traps you can fall into. Lastly, we have the DORA metrics, which are a fantastic way to measure DevOps performance. And in case you're interested in improving your DevOps performance and you're not using DORA, we recommend you adopt them. However, DORA does not measure productivity. Let's take a closer look. So we have in DORA 4 metrics. I know there's a 5th one, but let's just keep it at 4. The first 2 measure flow, and the bottom 2 measure reliability. In the context of productivity, since reliability needs flow to make sense, let's just zoom in on the flow metrics and take a look at why using the DORA flow metrics can be misleading in terms of using it as a productivity metric. There's multiple reasons, but the first one is that deployment sizes are not consistent within teams and also across teams. So if you're measuring the 2 flow metrics, right, if you're tracking these and you look at deployment frequency and lead time for changes, you're kind of missing an ingredient here, which is like how impactful or big is what is being deployed. Without this element, you can't really make sense of the other 2. Second, we found that these flow metrics are very often gamed in our research participants. And this is because once, management starts pushing people to increase their productivity, people start artificially making smaller and smaller deploys, funnily enough, reducing their productivity, even though in these metrics, they would show an increase in productivity. So it's possible to increase your DORA performance without increasing your productivity.
So to sum up what Yegor said, measuring engineering productivity is hard. So some people have given up on it, but we still think it's worth exploring it because we think how great it would be if we had a good metric that is fair, accurate, unbiased, and comparable. So if you imagine a world in which you had this, you could take better management decision, it would foster innovation, and it would motivate your top performers. Good people always want to work with other good people, and you're kind of up-leveling the entire team by providing a better and fair playing field. Now, before we dive in, I want to work a bit on definitions to make sure we're on the same page. So one thing is output, and the output really is the tangible work produced by the engineers. I'm not just including the engineers here, I'm including also all supporting functions. Think QA, product management, UI, UX, whatever you may have. And output is then influenced by velocity and building things right. Outcomes are things that are business results that stem from building the right things. And in order to determine feature prioritization, there's frameworks for it that you can run. So if I kind of map out that logic, we believe it makes absolute sense to focus on output because when we look at our participants, there is more or less a standard way to acquire data. Most of the organizations nowadays are on Git. So from an integration standpoint, it allowed us to get data across a number of organizations that is comparable. Second, we felt there's pretty mature product prioritization frameworks that do a pretty good job in helping teams determine what's the right thing. And our hypothesis is that all else equal, high output is better than low output. So if I'm mapping that logic out in 4 quadrants, so on the x-axis, you have business outcomes, and on the y-axis, you have engineering output. So think of it. You have a low-performing team, you're building the wrong things. This is not a good place to be. So then imagine you have a high-performing team, but they're building the wrong things, which means your business is not viable. You'll go out of business because you're not going to deliver the good results. Now, 3, that's an especially tough spot to be, because it might be a low-performing team, but they're building the right things. And then it might be you're lucky that you have a very strong business model that supports a lot of inefficiencies. And then people look at the outcomes and then they say, oh, our outcomes look great, so there is no reason to change anything, and you're stuck in this position forever. And in order to get into the high-performing quartile, you need a high-performing team, you need to build the right things, and what we're proposing is that it's equally important to measure both things. You need to measure output and outcomes, and only then you can achieve to be in the top quartile. So now I want to focus a little bit on the model and how we quantitatively assess the output measurement. So the step is to connect the Git repositories. We run an algorithm on it. The output then is aggregated. It's saved in a database. We can run some analytics. So I think the key distinction is here in part 2. So the key is not just counting things. So with modern technology, it is possible to get a deeper understanding of what's happening inside the source. We analyze each and every commit. We put it in context with the rest of the code base. We look at commit patterns. We look at all kinds of data points inside the code. So essentially, we try to understand what's happening inside the code, what's the impact on the rest of the code base, and then we combine that with the Git metadata in order to form an output metric. We can do that for 10 supported languages and frameworks, and having that broad compatibility, it allowed us to build up a big data set. So we have currently more than 50,000 software engineers in our study. We've analyzed millions of commits that in total are approximately 2 billion lines of code. And since most of our study participants are for-profit businesses, we got 80% of private repos versus 20% of public repos. What we like about that is that typically from businesses, we can get additional information on the contributors, such as do they work full-time, do they work part-time, what's their function, and it allows us to do further calibration and derive further insights. Our study is a long-term study, so our participants commit to stay in the study for at least 1 year. So it's a bit tricky to keep them engaged, and in order to achieve that, we've built a participant dashboard in which our participants can get insights, they can log in, they can see their current measurements, and they can get some benchmark data to see how they're doing relative to other study participants. Now, I think the elephant in the room here is, and a lot of people are probably wondering, so how did we test the accuracy of our model? Actually, we ran several tests. Today, I'm going to present one, which is also published in our paper. So if you're interested, you can read up more on this. So in order to test the accuracy, we assembled a team of 10 experts. Think, software engineering, senior people, more than 10 years of industry experience. We picked 70 commits from our data set, and we've asked them 7 questions that they needed to answer on all the commits. So some of you may ask, okay, why not 1,000 commits? Well, there is a practical reason. For example, it's very cumbersome to answer so many questions to so many commits. So we had to keep it practical to actually give our raters a chance to actually work through the entire questionnaire. So in total, we yielded 4,900 data points. After we had those, we also took our model and we asked our model to answer the exact same questions on the 70 commits. And in order to test the robustness, we did some leave one out cross-validation. So by doing so, we also got 4,900 data points. Now, analyzing the results, and for me, having worked in engineering, this is really a big surprise. When I was in meetings, I always felt it was very hard to agree on something. But it turns out the raters in our study, they had a very high agreement. So the intra-class correlation coefficient is greater than 0.8, which is really a very strong agreement. So for us, that was a big surprise. We didn't expect that. Then the next question is, okay, is our data set big enough? Because we had to make compromises to keep it practical for the raters. So we ran a power analysis, and essentially what the power analysis does, it tells you what's the probability of getting a different result if you had a bigger data set. So in our case, the probability is way lower than 1%. So we think we're in a pretty good spot. Now, lastly, we wanted to know, does the algorithm agree with the raters? What's the correlation there? So we ran that, and we got an R value that is greater than 0.85. So it's an excellent correlation. So both the experts and the algorithm are very much in agreement. So what that means for us is that we can do a lot of analysis on a lot of commits at a very high velocity. And also, after running that, we looked at our study participant data, and we looked at it in comparison to commits, lines of code, story points, all the other methods that they were using. And so I'm not claiming that this is the best way to measure productivity. Our method for sure has flaws, but what we're very confident is that it's a better way to measure productivity relative to these other methods that we explained in the beginning. Now that we've worked a bit through the science, let's move over to case studies that we have run based on our study participants' data.
We have 2 case studies for you today. And before we dive into them, I want to preface these that they're meant to illustrate the power of what happens when you combine our measurement with other sources of data. This enables you to reach deeper decisions because you can have, kind of more decision vectors to look into. So here, for example, we have 2 teams, Team A and Team B. They have the same headcount and they are within the same company. But Team A, as mapped in this chart, so basically you have quarters on the bottom, and the y-axis would be output units. So think how productive they are. Team A seems to be performing better than Team B in isolation. Given that they're the same headcount, then one might reach the conclusion that Team A is better. However, when we connect it with financial data, the story changes a bit. So in this case, we can see that even though Team A performs better than Team B is 40% less expensive. The cost is 40% less, which means that when you do a cost per output analysis, well, actually, Team B is 30% more cost efficient. Whatever you choose to do with this data, that's beyond us. And this is like a very simplified case study for illustration purposes. Our charts look a bit more fancy than this. But it's meant to illustrate the point that, hey, without this connecting it to financial data, I would have maybe then did the wrong decision, right? Next case study is a really interesting one. It's about a startup that received VC funding. And here we have in brown is the headcount. And you can see that around the end of 2021, they received this VC money injection, which made their headcount basically triple overnight. It's a very common story here in the Valley. The orange line shows output per contributor or per person, basically how efficient the team is. And what we see is that as soon as the team size triples, output per person plummets. And what's most concerning is that it doesn't recover, and in fact, it even keeps trending down. If we look at some of the data, we can see here that the team size grew by 3, the team cost also grew by 3, but the team output only grew by 1.5. So then, is this a good deal? I don't know. But what it's meant to illustrate also is Brooks' law, which basically says that throwing more bodies at a problem isn't necessarily going to make the problem be fixed faster. This is especially true in software engineering. Now that we've seen these case studies, we can take a look at what else are we working on currently. And the first thing I want to point out is that we are currently investigating how we can power our method with LLMs to make it even better. Secondly, we're looking to continue running a cross-language validation of our measurement, which means basically running the same exercise with the 10 raters, except for different languages, and continuing to improve the accuracy of the model. And then thirdly, we'd like to release a scientifically objective paper that discusses the pros and cons of our method in comparison to other methods, right? Both the good, the bad, and also the ugly. If this sounds interesting to you, there's ways in which you can get involved. Number one, you can become an expert rater in case that's interesting to you, which means you would be looking at these commits and giving your professional assessment on, that commit and some of their attributes. Two, you can choose to join the research with your organization and be a research participant. And three, we would sincerely value your feedback on our latest paper. We know there's a lot of brain power in this room, and we think that with your feedback, we can make the next paper even better and continue to improve our model. You can access all of these things by scanning the QR code, which will lead you to our research portal. And there's going to be links to each one of these things. With this being said, thank you so much for your time today. And I would like to open up the floor for questions.
Thank you.